So good morning everyone. I'm Kantee. I will be talking about running the BSD Kernel TCP IP stack in Userspace. Of course, the first question is, why would someone want to do it? Well, that's a good question. It's usable for things like virtualization and debugging, development. If you happen to need something which uses the kernel sockets layer in Userspace. For example, my original motivation was to run the kernel NFS client in Userspace, and that needed the kernel sockets layer, and then that link led to one thing, and that led to another thing, and then I actually ended up. I can have the kernel TCP IP stack as a library against an application. So let's start with the old thing, kernel code. Why is kernel code considered special? Yeah, I don't actually know. Because it runs in the kernel. Yeah, exactly. But why is that special? It seems to be this great big mythic thing. And for example, a common conception is, if it's in the kernel, it's fast. It's, for some reason, it's automatically fast if it's in the kernel. If it's in Userspace, it's automatically dog slow. Well, that's not really necessarily always true. You can write crappy kernel code, and you can write good Userspace code, and kind of the point is how many context switches do you need to do to access some pieces of information. But one actually good reason or good justification for putting code into the kernel is that your code uses privileged CPU instructions. So if you try to execute those instructions when your CPU is not in privileged mode, not so good. But as it turns out, the amount of code which uses privileged CPU instructions is very tiny. And for the rest, there is no real need to run in the kernel. Well, there's also the kind of administrative boundaries approach. So if you think of your operating system as an arbiter of resources, and then you have some physical resources like a network card or something like that, and then your kernel can control, because it's in a separate privileged domain, it can control who has access, when someone has access, why they have access, and so forth. But these are kind of the main questions I think of when thinking of kernel code or Userspace code. So my talk today will consist, I'll briefly introduce how you can run the TCP IP stack in Userspace. What do you need to do to send and receive packets, which is fairly important if you're doing networking. Then I'll tell how you can actually configure the Userspace networking stack, so you have your own IPs and routing tables and so forth, and a few examples of well, actually I think I forgot to include this in the slides, so mainly a few examples for testing. Then we'll briefly look at some performance figures and do conclusions, whatever that is. Okay, so the thing I've been working on NetBSD for the past 1.5 to 2 years is this idea that since most of the code isn't or doesn't use privileged instructions, isn't necessarily involved in administrative boundaries, you can run it anywhere, and it's directed at running kernel code in Userspace. Most people, doing it the other way, running Userspace code in the kernel, most people would argue that that's probably not such a good idea. It wasn't really written for the purpose, and does crazy things. But the other way, it sometimes makes sense. Yeah, and the naming. Well, I guess it's a fun story. So when I was importing this originally in August 2007, the hardest part was, of course, figuring out a good name. And well, then at some point David Holland suggested that maybe you can use RUM for it, like runnable Userspace module, as opposed to loadable kernel module. And I thought that was a good idea, but then, as it turned out, we already had a driver in tree which was called RUM, which kind of ruined my perfect plan. And then I shuffled the thing around in my head for a bit, and then I decided to name this after food. Like, well, a rump roast on a cow is from here. Of course, then later someone told me that it's the name rump is just not limited to cows, that it's used, for example, for describing human parts too. But then it was a bit late at that point to change the name. And then I figured out a fancy backronym. I have no idea what MEDA stands for, but it was the only word I could think of which started with M. Actually, maybe I should have used meat there. So what's the big picture when we run a kernel TCP IP stack in Userspace? So we have a process, and we have our kernel code as a library as part of the process, and this process context includes all of this kind of TCP IP stack state. So you have your set of interfaces, you have your interface names, your interface aliases, your routing tables, your, I don't know, syscontrol variables, your this, your that. Everything is kind of already in the of the process, and kind of the application runs in the same process. And to access the kernel, you just make function calls from your application code to your kernel code, and then, well, they are prefixed rump_sys, and they do exactly the same as their real system call counterparts. For example, rump_sys socket would open a socket, but it would open the socket state here, and it would pass a file descriptor from this library kernel state. So the real kernel actually doesn't know anything that our application has opened a socket and so forth. And then only in the case when this kind of userland kernel needs to do something like I/O, then it actually executes real system calls to the real kernel. But that's all kind of behind the application layer, so it's done somewhere here. So the application only talks to this guy. And the application might, for example, be, the application might, for example, be actually it wouldn't. I was gonna say it could be the NFS client, but since the NFS client is already part of the kernel, then it wouldn't be, but it could be some application which is using NFS through the read-write interface to access files on an NFS server. Oh yeah, so what I already just about mentioned, we can use kernel code directly in Userspace, and we have to implement a small amount of glue code to allow the kernel to function. For example, in the kernel, when you allocate memory, you ask for a page from the VM subsystem, and of course then on top of that you have your kernel memory allocator. But basically you need to get memory from somewhere to be able to allocate it. And this glue code thing, stuff like maps the request to allocate for a page to mmap of an anonymous memory and so forth. And the system, it's available on NetBSD. It requires quite a bit of changes to the source tree, which have been going in during the past, over 1.5 years. So kind of the idea is portable, but porting it isn't necessarily very easy. kind of if you want to try it out, you want to use current, but there's also some support in the 5.0 source tree. But as it turns out, since this is Userspace, you can also use the current kernel code on 5.0 with some restrictions. I'll come to those a bit later. And it's a very slippery target, since I'm doing something, then that's a silly way to do it. Let's do it completely differently. So there's really no compatibility yet or things like that. So then, running kernel code as a Userspace process. Now for some, this might sound a lot like a user mode operating system, like user mode Linux. Well, yeah, they technically do the same thing, but it's a really different approach, where for a user mode operating system you take your entire operating system, your kernel, your processes, your root file image, your init process, your I don't know what process, blah blah blah, and you want to run everything. So you actually have a copy of your operating system which is indistinguishable, well, as far as possible indistinguishable from the original. As here, I kind of built it from the opposite way. So I took the minimum which was necessary to get my functionality working in Userspace, which at that time was the file system code, and then it expanded a bit. But this approach avoids for like if you're interested only in using your kernel code as a library in a Userspace application, you don't want to have your own root file system image, you don't want to have your init processes if you're not interested in those. All of that stuff, you can just forget about it. It's not necessary here. And one cool thing about this is that, well, I came up with a nice term. I call this kind of kernel virtualization as first-class virtualization, because your kernel is indeed kind of directly controllable from your host operating system. You can, kill a process. You can attach GDB to it. If you want to make a system call to it, you don't actually have to have a process running inside your virtual operating system. It's a process running on your same system. All that stuff. If you want to use it, you don't need a full-blown configuration. This is my operating system, this is my root utilities, this is my root password, and so forth. So this doesn't support processes at all. This doesn't really support users in the classic sense, and so forth. So what's the penalty we need to pay for this lightweight operation? Well, obviously there's the thing that if you want to use something or like test something which has many processes, does fork, does exec, you can't do it. But the other penalty is this kind of depends on how the module structure of the kernel is well structured. So I kind of pick, this is a good module, this is a good module, this is a good module, these modules do fun things, these modules I don't care about. Now that works very well in the case where your set of modules is a closed set, so they don't make any calls over here or over there or over here. And if someone changes one of these modules and actually introduces a call to some other part of the system, then things tend to break a bit. I eventually hope to figure out some way to make this less delicate, but so far I've been unable to. If anyone has any brilliant ideas, I'm of course all ears. This is probably the same slide for the third time, but most kernel code is just algorithms. We don't need to do anything special for them. But then we don't have stuff like raw network interface accessing Userspace. Maybe we could get that, but I'm not sure we want to for this purpose. So we need to figure out some emulation layer. And all of the code in this system is machine independent, so there's no need to port for it for a specific architecture. It doesn't, because it only relies on what a process provides in Userspace, and the process things provided by the system libraries, the kernel to a process, are already machine independent, so we don't need to do anything extra. There's 10 lines of machine, well, okay, maybe 20 lines of machine dependent code currently, but it's just to satisfy the kernel module ABI. So there are two ways to use this. Either you can compile your kernel code as a position independent library and then link it, or then you can take on i386 and AMD64, you can take a kernel module and link that directly against your application. So for accessing the network, we have two different possibilities. We kind of have a iNet sockets internet emulation layer, which is good for consumers which are interested in using the in-kernel sockets layer. Like I said, this was originally done to run the kernel NFS client in Userspace, and the kernel NFS client uses, well, sockets. So we need some interface mapping from the kernel sockets layer to the things which the host process can actually access. So I wrote a small module which I called SOCIN, which just maps the protocol user request, what do you call them? Well, the protocol user request protocol to socket system calls. So for example, when you get a user request for connect, it just does the connect system call, and that then maps to the host kernel connect system call, and then you actually get network access that way. The good thing about this is that since it uses the host TCP IP stack, you don't need to do any configuration. Like you don't need your separate IP address, etc., etc. I guess you could do port mapping at this stage, so you could actually have your own set of ports in here, but currently they're just kind of, it uses the host system's ports, so if you have many of these you might get port collisions, but I might fix that later. Yeah, but of course if you're interested in having the TCP IP stack functionality as part of your Userspace process, then this model doesn't help much. So then we get this kind of full TCP IP stack in Userspace, where you actually have the kernel sockets layer, the kernel TCP IP code, and then you need some method of accessing the actual network. So you have some sort of interface driver here which behaves like an Ethernet driver, and in this case talks to the Ethernet tap driver in the kernel, does just read-write calls and sends raw packets and receives raw packets that way. But this requires a dedicated IP address for this stack. It requires special configuration. It also requires access to the tap device. For example, if you don't have super user privileges or the tap device is inaccessible on your host system to normal users, you can't use this, then you have to. This can be used without any privileges, so just normal socket privilege use is enough. So for this virtual driver here, there's actually two possibilities now. The other one isn't mentioned in the paper. I wrote that last week or 2 weeks ago. It's still a bit shaky, but maybe I'll improve. So we have the tap interface, which you can use to attach to a real network. And if you use the bridge driver to connect it to an actual Ethernet interface, then your packets flow in and out of your virtual TCP IP stack or your Userspace TCP IP stack without any problems. And then I wrote kind of for massive testing I wrote this shared memory interface, which doesn't use any kernel services. It uses shared memory as a bus. So if you have multiple processes with their own TCP IP stacks, you want to do some testing and make them communicate with each other, you can, you know, build a entire network on your local machine. And well, this is supposed to be more lightweight, but I don't know, I didn't test how much more lightweight it is yet. Maybe it completely sucks and then I'll just have to remove it, but we'll have to see. And for the shared memory interface, you can't have direct external access, since you can't, you know, bridge a bunch of process shared memory to a network interface. But what you can do, if you have a network of these, then you can have kind of like a, what should we call it, a border TCP IP stack. So you have a bunch of these networks, then you have all your routing going into one, which actually uses the virtual tap system, and then you can route your traffic through a bunch of TCP IP stacks and a bunch of processes and out to the real network from a single machine. So since this is a technical conference, let's give a few technical examples of what's necessary to emulate the kernel. For some reason, I don't know, these are probably a bit boring. All papers discussing running TCP IP stacks in Userspace or so forth always seem to be compelled to explain these same things, so I'll be compelled to explain them again. So locking and threading. So yeah, well, the network stack depends on locking somewhat, and as it turns out, we already have a locking interface in Userspace. It's just called pthread mutex instead of your kernel interface name, but otherwise it does exactly the same thing. No difference there. So instead of implementing our own locking system, which complies with the kernel locking, we use locking and threading from pthreads. So, for example, a kernel thread create is actually a pthread create, and kernel mutex lock is mapped to a pthread mutex lock, and that way you get automatic scheduling also. So the pthread scheduling takes care of scheduling your kernel threads and so forth. There are some differences with the kernel in this. For example, the pthread threads get scheduled whenever they want to, instead of being scheduled explicitly like in the kernel. But with a preemptive kernel, or mostly preemptive kernel, I haven't really noticed any problems with that. When I was first doing this, I forgot to implement support for the big lock, which kind of made things work less than nicely. But once I figured out what was going wrong there, then things have gone pretty smooth. Then we have soft interrupts. So the kernel networking stack defers some processing. You know, when you get a packet, you process it up to some point, then you figure out, okay, this is going to IP processing for next, but I'm not gonna execute this in interrupt context. I'll schedule a soft interrupt for later processing, so I don't need to run in this mode for long. And well, in Userspace, we really, the way I've done it, we don't have interrupts at all. We kind of technically have interrupts, but actually they're all threads. So, for example, when you create a virtual interface, it creates a thread which just pulls the tap driver and reads packets from it continuously. When it gets a packet, then it just does a function call. So it does have a thread context. So basically, we could process soft interrupts directly, but as it happens, the code is structured so that it first schedules a soft interrupt and then it puts the packet on the queue. Which, if you try to actually do the processing in the soft interrupt scheduling, you don't have the packet on the queue yet, so it ends up doing nothing. In the kernel, this isn't a problem because, or there's no races here, because when you schedule the soft interrupt, then the scheduled soft interrupt is executed only after your real interrupt handler returns. And I actually wrote in the paper that it doesn't emulate this. The soft interrupts are executed in a separate thread, and it doesn't accurately emulate this condition that the soft interrupt is executed on the same CPU. But I wrote in the paper that I've not noticed problems due to this ever. And now that I started thinking about it, I think for those who were at the NetBSD BOF on Friday, my demo kind of failed at first. So I think it's because of this emulation inaccuracy. So I think I'll have to emulate it better. And then we have stuff like timers for TCP processing. They're necessary. So if your packet gets lost somewhere, you need to resend it. And well, those are all based on getting a clock interrupt, and a clock interrupt is delivered by a thread. Okay, that's a good sign that you've been talking too long. Screensaver hits. Yeah, they kind of just have a thread which does clock interrupts, and there's some things I won't go into now, but this isn't, once again, completely accurately emulated, since you're supposed to get a clock interrupt on every CPU, and now we only get clock interrupt kind of on one CPU because there's only one timer thread, but things kind of work. Yeah, so the application interface to the Userspace kernel or Userspace TCP IP stack. So just you access it by doing regular system calls, but instead of doing system call foo, you do rump sys foo, and that's the way to differentiate where it should go. There's a few issues due to this. This is technically, well, I presented a few options in the paper, but I still like to think this of mostly as a source-only interface. So it's fairly easy to port existing applications to use the Userspace TCP IP stack instead of the kernel TCP IP stack, but there's some things like the read and write system calls where you really run into trouble due to the fact that they're kind of overloaded. Let's say you can use them for files, you can use them for sockets, you can use them for pipes and so forth. So you can't direct all read calls to the application TCP IP stack. And kind of doing a source editing and recompilation allows you to pick the right ones. I know I'm not totally happy with it, but it's what we have currently. One implication of this also is that you can't use it for, like, for example, a jail-style virtualization where you have the policy of which TCP IP stack you use is directed by someone else than your application. Like now, since the application makes the choice of which TCP IP stack to call, then you can't force it to call only that one. And configuration, if you have the full TCP IP stack, you need to configure it. You need to have an interface, you need to configure an IP address for your interface, you need to configure your routing tables, and here's an example of, well, a fairly limited example. There's a full example in the paper of how to configure at least the IP address, but the routing is the same. You open a routing socket, then this 3 dots is a very good representation of building the routing messages. You build the routing message, and then when you've built it, you write it to the socket, and then hopefully you have your routing configured. So a few words on portability. Well, since this is kernel code in Userspace, it theoretically is portable. It's easy to make run on everything, but running the code isn't the problem. The problem is interfacing with the code. So when you have the same version of the same system, like for Userspace, and the kernel, well, okay, everything is the same. But if you have 2 different versions of a system, the kernel headers installed in Userspace, user include sys, might be different than the ones which were used for the kernel compilation, and they might have some differing values. Well, this probably won't change, but recently in NetBSD we had time t change from 32 to 64 bits. Now, if your application has a 32-bit time t and you have a pointer in some rump system call and you make it to a kernel which has a 64-bit time t, things don't work so well. And the problem is that it's not really easy to kind of have a namespace in C for any of these symbols. You can't include headers from 2 different trees. So if you try to include kind of headers from your native tree, and then, or let's say we have NetBSD and FreeBSD. So in your application you include normal headers, which includes some sys headers on FreeBSD. Then you want to make a kind of call to the virtual TCP IP stack running based on NetBSD code. You can't include the NetBSD system headers, because then you have like a ton of conflicts. You have multiple symbol definitions, everything. So things break down. So while in theory it's portable in the sense that it runs, it's still kind of it's work in process to have interfacing to it portable. If you want to do just some limited things, it's not really difficult to write a bit of code which exposes the right symbols, but for the general case it doesn't currently work. So testing and development is very nice. Well, there's one exception. Currently NetBSD our thread support in GDB isn't that good. So last I tried it doesn't really correctly handle breakpoints for multi-threaded programs, which may be a problem for debugging this, since this is mostly a multi-threaded program. There are, some ways you can disable the thread creation, but it's all very kind of, how should I say it? Kind of, if you need to debug some area, you need some specific hacks. Of course, this is more like, I wish someone would have enough time to fix GDB on NetBSD, so then I wouldn't have to worry about this anymore. But for debugging, still you can do stuff like, you get a application core dump, so you're trying to debug something, you put prints, or then you put, if you want to figure out if you run across some path, you put a panic just in there, and then, well, what I usually do, I put a panic somewhere, and when you're examining a core dump, then threads happen to work. So then I can examine the state of all the threads. This is actually another thing I use frequently, which is kill minus abort, so it aborts the process and once again creates a coordinate for you. Most cases are the same as in a real kernel, but for example, if you're trying to debug timing issues, you're trying to debug some interaction with a hardware driver, then this is maybe not applicable. Or there are a few shortcuts in the emulation, although now I can't actually name any. But there's a number of things where the kind of the behavior of the virtual TCP/IP stack is not exactly the same, but it's corner cases like timing and so forth. So if you're just trying to look at where the like what TCP input does, then it's exactly the same. And since the kernel and the whole operating system is a process, you can run these things pmap. You can even run valgrind, although I don't know, NetBSD support for valgrind seems to be a bit unexisting again. I remember when I was first working on this, I did successfully manage to find a memory leak I was looking for when I was trying to get the FFS code working with valgrind, but then I lost my source tree somewhere and then I never bothered to revisit that. So this is an example presented in the paper. It's just for simple one machine routing cluster testing. So we have a simple application which just sends a timestamp through a UDP socket to another machine or another IP address, and these are all their own processes running within one machine. So the first process has the client, has its TCP/IP stack, has its virtual interface, then they are bridged together. Then we have a process doing purely routing, which has two interfaces, and it gets the packet, sees, aha, it's destined for this guy, so then it routes it through the other interface, and this guy then receives it through the normal path, says, aha, we got a packet, let's respond to it immediately, and then sends it back. And well, this is an example of something you can do. It's not limited to 3 nodes, but that's easy to draw. Of course, when I went from 3 nodes or kind of one routing node to 2 routing nodes, I noticed I actually had to configure the routing tables also, because here they're kind of implicit. So this receives a packet destined for this machine, which happens to be on a subnet the TCP/IP stack already has. But if you put another router here, then this guy doesn't know how to route to that one, so you actually need to configure the routing table. It took me a few minutes to figure out why 4 was so difficult. A few words on performance. My common excuse is I'm still trying to figure how to do this right, so I haven't spent much time optimizing it yet. So like if you read the paper, it does perform fast enough for most purposes. For example, it can saturate my home network with a Userspace TCP/IP stack. Of course, my home network happens to be a 100 megabit network, but it still saturates it. So it's fast enough to be useful. I have a performance figure on the next slide, and here's just to explain what's happening in there. So I ported TCP to the rump virtual networking, and I have a kind of native TCP process running. It just does socket communication. That's sent to the actual networking interface on the host, which is bridged to the tap driver, and then hence received by the virtual interface running in Userspace, and then you get TCP/IP socket processing, and then the packet is received, and then so you kind of have 2 TCP/IP stacks running on your machine. one which is the actual real TCP/IP stack, and the other is the virtual one. So I just did a benchmark against QEMU, and it was approximately 10 times faster. So then I didn't bother doing anything else anymore. Well, of course, QEMU is translated code, not native code. RAMP runs all code natively, so I don't know if the comparison is fair, but before I wrote RAMP, I used QEMU, so in that sense the comparison is fair. And of course for QEMU, kind of this same diagram applies, so just instead of having it directly as a process, you have it as a kernel running inside of QEMU. And then in QEMU you also have a separate process which contains the application, so you have kind of more indirection there. Yeah, that's my bad conclusion slide. This is my better conclusion slide. So most of kernel code doesn't care if it runs in the kernel or not. I'm trying to make it possible for most code to be what I call environmentally independent, so it doesn't. There would be no special. Like, so some code needs to run in the kernel, but most code can be independent of the environment it runs in. And there's a number of reasons why we want to do this. Userspace is naturally an easier place to test things. You get some sort of isolation. Then if your application you have an application which actually needs a TCP/IP stack, then it's good. I have one potential example I mentioned in the paper, which currently uses QEMU, some other emulator, but I naturally think it would be more elegant to do this way. And performance is enough for current needs. I think it can be improved somewhat. There's of course the problem of kind of, at some point it starts depending on how you actually access the real network in Userspace, which is currently done through the tap driver, and I think that might be the limiting factor of how fast this can go. But then we can start adding things if that is a problem for someone. If you want to look at the code, it's in the NetBSD tree, fairly self-contained under sources sysrump. And there's a little web page which attempts to summarize most of the important things. And, you can ask on the NetBSD mailing lists. Thank you.
Did you try QEMU with kernel accelerator module or not?
Yeah, the question, did I try QEMU with the kernel accelerator? Yeah, the answer is no, because I don't know if that works on NetBSD or not.
Oh my gosh.
Yeah, I probably should have mentioned it. Yeah, I know it's probably going to be faster.
QEMU guy says with kernel accelerator module, QEMU can maybe 2 times or 10 times faster. So with KQEMU module, your benchmark result turn in the very drastic change in the result.
Yeah, I would expect using other forms of virtualization like Zen or things like that, which doesn't use translation to provide the emulation, then of course it would perform better. That is absolutely true.
Yeah, absolutely.
So do you hold anything other than TCP/IP out? File systems or kernel processing or any of that?
Yeah, I pulled file systems. Well, there's kind of two main things. There's file systems and then there's networking, and I haven't found much use for anything else. But then again, what else is there in the kernel? There's the device drivers, which are device drivers, then there's virtual memory, and that's about it. So, yeah, most of the file systems do work. I think Like things like procfs don't work, but in Userspace well, you maybe could make them work on a limited scale, but that would be a lot of work. So, but all the kind of real file systems which just interpret a file system image, they work. The temporary file system works, although the temporary file system may not be that useful for Userspace. But the other file system stuff is kind of useful because you don't need kernel support for a file system at all anymore. And if, for example, you have an image, a file system image, in some cases, if you do the interpretation of the image in Userspace, you can get better performance than if you use a kernel file system, because you don't need to do so many system calls. But then you can't mount the file system, so it's kind of limited to your one application. Everyone else is too hungry. Eric is not.
I think maybe I'm not completely understanding the motivation. The idea here is that you can hack on the TCP stack on a running system and basically debug changes and then drop them into the kernel, since that's a hostile environment for debugging.
Yeah, debugging in Userspace is one of the motivations.
So
testing is kind of the main motivation for the TCP/IP stack.
Okay, so the applications that you want to run again, you actually have to link into the process with the run library, as opposed to something where it like somehow grabs system calls from other real system processes and says, okay, I'm going to use this TCP/IP stack instead of that one.
Yeah, no, that's not currently possible. Kind of, you need to explicitly say that you want to use it.
Okay, so this isn't like a attempt to do microkernels where you move the TCP stack into it's not a process. Goes around another.
Well, it's usually a server. Well, no, not yet at least.
Okay.
But I see no reason to remove the TCP/IP stack from the kernel for the general case.
Well,
Yeah, but I see no reason to do that. Like I don't want to completely strip it out. I want to have a kernel TCP/IP stack also. I'm just saying that it's possible to use that also in applications.
The good thing about microkernels is that the stack crashes, not the whole machine crashes.
Yeah, well,
you can't use the machine, but
yeah,
it's still up. Theoretically.
yeah.
If the TCP kernel process crashes, you might be able to restart it. All the connections reset, but then you can still get into the box. So less catastrophic. If it crashes and doesn't come back, obviously you have to walk to some place to kick it.
Yeah, this is true.
It's a minor advantage, potentially.
It's just probably not the place to have the microkernel or not microkernel.
Yeah.
Yeah, I didn't. Yeah, we go final joke.
On the other hand, over drinks tonight.
We could probably find more interesting things to debate over drinks. Does this? Would you be able to run like a FreeBSD stack on NetBSD or vice versa with this technology, or would that be a lot of work?
Well, you need similar support in FreeBSD, and like I said, it's not a lot of work, but it's a lot of little changes. But yeah, theoretically you should be able to run the NetBSD stack on FreeBSD. But like I said, you can't necessarily, for the general case, interface with it. Your structure layout is different, your you know, this variable is, or this type is of different length. This macro has a different value. Okay, thank you.